Okay, so we're going to continue on in Chapter 4, and we're going to talk about linear regression. And the idea behind linear regression is that we're trying to fit a straight line with an equation to a set of data. So in our textbook, the example they use is that we have an x variable and we have a y variable, okay? And the x is the number of pages in a book, and y is the thickness or width. And the idea is we use the x variable to make a prediction for y. Okay, so we will use the number of pages in the textbook or in the book to make a prediction for how thick the book is. Okay. And so when we gather data, we're going to put along the x-axis the number of pages, and along the y-axis the width of the book. Okay? So a dot down here represents what? A book with a few pages, low number of pages, and the thickness is low. Okay, so this is a book with few pages and is thin. And over here would be a book with lots of pages and is thick. Right? High width, high y value, high x value. Okay? And we have other points, etc., etc., etc. Something like this. And so we're going to try to fit a line to the data. Okay. When we come up with the equation of a line, okay, so in algebra, we write the equation of the line y equals mx plus b. Okay. So in statistics, we got to mess with you. And we're going to use y hat is equal to a plus bx. Okay? The hat, which is this thing, on y, means it is a prediction. To distinguish it from actual data points. Okay, the little hat, this little thing, that is means it's a prediction. A is our intercept. And B is the slope. Okay. So for our example, the general trend is that books with more pages tend to have higher thickness or higher width than books with fewer pages, right? So general trend is positive. Books with more pages tend to have higher width, and vice versa. Okay, so books with more pages tend to have higher width. Books with fewer pages tend to have lower width or lower thickness.
What does the A stand for?
A is the intercept. Okay, right? In algebra, you learned straight lines, you have a slope and an intercept, right? So algebra, the slope was m and b was the intercept. In statistics, we write y hat is equal to a plus bx. A is the intercept and b is the slope. So in our case, okay, I'm just going to leave it in this same form. I'm not going to put in actual values for a and b just yet, but y is the width, okay? So I'm going to just replace the letter y with the word width, and I'm going to put a hat over it, okay, to indicate predicted width. Predicted width is equal to a plus b, and what is x? B times the pages, okay? This is a star to indicate, maybe I should erase that. B times the number of pages, okay? Or pages, we plug in a value. So we might have an actual data point, let's say an actual data point may be is that a book has 400 pages and the width is 27 millimeters. 27 millimeter width. Okay? So this is an actual data point. I'm going to just plug in values for the intercept and slope, okay? And these come from the book, and so we will say width, predicted width is equal to 6.22 plus 0.0366 pages. Here, let me just cut that and slide that up just a tiny bit. Okay. So if we were to use this equation, this is our prediction equation. Okay. The actual data point was that a book with 400 pages was 27 millimeters wide or millimeters thick, okay? We could ask, what would we predict the width to be for a book with 400 pages? Well, what is our prediction? Okay? Well, according to this, our predicted width would be 6.22 plus 0.0366 times 400, right? we're going to plug in 400 for the number of pages. So the predicted width, I go here and I do 400 times 0.0366 plus 6.22. And according to this equation, we predict that a book with 400 pages is going to be 20.86 millimeters thick. Okay, so according to the equation, we predict that a book with 400 pages will have a width of 20.86 millimeters. Okay. Is that okay with everyone? Yeah, those I just pulled from the book. Okay, I'll explain how we get those numbers later. Okay, but at this point, don't worry about where 6.22 and 0.0366 came from. Okay, prediction equation. So this came from the book. Okay, but we're going to plug in. We plug in 400 into pages and we do our calculation. Okay, and so it says we predict that a book with 400 pages will be 20.86 millimeters. Okay, and so that means if I go up to the line at 400, this would be right at 20.86, okay? But we have a data point that's at 400 but is at, 27 millimeters. Actual point at 400, 27. Is this okay? All right, so let's take a closer look at some of this stuff here. Okay, so this is our equation here. All right, so in this case, what is our intercept? This is our intercept. And 0.0366 is our slope, okay? The definition of the slope. What is the definition of the slope?
Rise over run.
Okay, everybody says that. The definition of the slope is actually, all right, I mean, yeah, rise over run is fine, but I don't think that means anything to you guys. What does that mean? Rise over run is 0.0366. What does that mean?
It goes up.
Okay, so it goes up 0.0366 and it runs 1, or rises. So what does it mean to run 1 here?
On the X.
Yeah, okay, and so in our case, our X is
1.
pages. Okay, so here, the definition of the slope is how much y will change when x changes by 1. Okay, and in our case, because we're making predictions, it is how much we predict y to change when x changes by 1. Okay, so for statistics, or because we make predictions, the slope is how much we predict y to change if x changes by 1. So what does it mean for x, or the pages, to change by 1? And I think I heard the correct interpretation over here. So in our case, what we're saying is that if we increased, or if we looked at 2 books, okay, and one book had 400 pages, okay, so one book has 400 pages, and we predicted, what did we predict? We predicted the width.
How many millimeters per page?
Yeah, the width is 20.86 millimeters thick, right? Okay, so if another book has 401 pages, okay, so we increase the pages by 1, we predict the width will be what? Width is 20.86 plus 0.0366. Okay, so basically the slope is how much the width is expected to change for each additional page. Okay? Or another way to think of it is the thickness of each page, okay? In a kind of a practical sense, okay? Okay. But if you just think of it as the slope is how much the width is expected to change for each additional page, I'm perfectly satisfied with that interpretation, okay? Or if you say the thickness of each page, that's also great, okay? Does that make sense?
Yes.
The slope. So I know you got it, but I also want to make sure the rest of the class has it.
Yeah.
Okay? So if we increased the width by, or if another book had 500 pages, so that's basically 100 more than 400 pages, how much would we expect the width to increase?
0.0366 times 5.
Yeah, this is 0.0366 times 100, right? Because 500 is 100 more than 400. So we'd multiply that by 100, and we would expect the width to increase by 3.66 millimeters. Do you guys follow that? Do I need to write that down? Yeah? No? Maybe? Okay. So I'll just say another book has 500 pages, okay, which is 100 more than 400, okay? So our prediction for width will be 20.86 plus what? 3.66 millimeters, okay? And we got 3.66 is 100 times the slope. So 20.86 plus 3.66, 24.52. So it's how much we expect or predict y to change if x changes by 1. If we add 1 to x, how much will y change? Is that okay? Let's do this again. Oh, yeah. Okay. Are we good? Are you guys able to see in the back row there? You guys are taking notes? All right. Now it's the end of regular season basketball. It's 2 playoff spots left. It's Pacers versus Nets, competing for the last playoff for the NBA. Those of you who don't know what I'm talking about, Pacers in Brooklyn competing for the East, and Oklahoma and what? It's Brooklyn Nets now. Yeah, they moved. They moved to Brooklyn. Yeah. What's that? Is it Hawks? No. Wait. Oh gosh, how do I not remember this? Oklahoma and New Orleans. New Orleans. Yes, thank you. NOLA. Okay. The Pelicans, bringing back. All right. Anyway. Yeah, I know. The Hornets to the whatever. Okay. They do. All right. Okay. So let's. Oh no. Where did this? This is what I want. Okay. So we want. Let's talk about the intercept. Okay. The intercept would be our prediction for y if x were 0. Okay? Sometimes it does not always make sense, or it does not make sense for x to be 0. Okay? And in those cases, then the intercept doesn't really make sense. Okay? But if it does, it would be the prediction for y if x were 0. So what this means is what? In this context, the intercept is 6.22. And what does that mean?
It's where the best fit line crosses the y-axis.
Okay, so that is correct, but using this, what we have here, the intercept is 6.22. So what is our prediction for y? Y is the width of a book. So that means if a book had what? if a book
Oh, 0 pages.
had zero pages, okay, meaning x equals 0. If a book had 0 pages, we predict the thickness, the width or the thickness, width would be 6.22 millimeters. So maybe one way to interpret this is the thickness of the covers or something of a book, okay? Because how many books have 0 pages? Generally none, okay? It's not called a book if it has 0 pages. But if a book had 0 pages, you know, so in that case it doesn't really make sense, but we can also visualize a book with 0 pages, right? I could just tear out all the pages in a book because I'm angry and I feel destructive or something. It's not the best way to express your anger, but if you decided to tear pages out of a book and you had 0 pages left, our prediction would be that the book would still be 6.22 millimeters thick, okay? Now, in other cases, like if we were trying to predict the weight of someone based on their height, it would not make sense to have a person of height 0, okay? Because nobody can have a height of 0. Even as a zygote, you have a non-zero height, okay? And you know, does that count as a person? Yeah, you know, that's okay. That's a whole nother realm that cannot be answered with statistics. Okay, so there are limitations. As much as I love the subject, there are limitations. It can't answer ethical questions, but it might be able to point you into whatever. Okay, we're not going there. So anyway, the intercept is our prediction for y if x had 0, was 0. All right, so let's check our understanding, okay? And so here we are going to do, here's a picture that's not going to be very good, but it looks like this. And we looked at a whole bunch of different cars, okay? And it looks something like this. All right, and the regression equation, okay, so in our case, y is the value of a car, and over here we've got the age of the car, age in years, and the value in dollars, okay. And so I'm going to write value with a hat over it is equal to 21375 minus 1215 age. Okay. So
What's in parentheses next to value?
a dollar sign. Dollar sign, because we are in America and we use dollars. Or any other country that uses dollars, I suppose. But we are in the United States for this data set. And so, okay. So this is the predicted value of a car, a used car, based on its age. We're trying to predict its value. Okay, so let's just try something out. Okay, how much do we predict a car to be worth if it is 8 years old? Using this equation here. So go, take take a moment to calculate this out. Is that what we got? No?
Yeah.
Too slow? Alright, so what did I do? I just plugged in 8 for age, right? So I'm doing 21375 minus 1215 times 8. So I get 21375 minus 9720, and we get 11655. Okay, so we predict the 8-year-old car to be worth $11,000, $11,655. Sure. So your 2007 Toyota Camry, maybe, I don't know. Okay, we don't know what model car this is. Okay, so other factors go into the value of a car. Okay, so what do we predict if the car was was 2 years old? Okay, so let's just do same question, but 2 years old.
18,000.
Yeah, that's the answer. Okay.
Will there ever be like missing parts of this that we have to plug in ourselves in different ways?
I'm not. Hang on. Okay, so well, all right. Let's just do this. Okay, so get your answer. All right, and the answer is equal to 18,945, right? So how we predict the car would be worth $18,945. It's our prediction. It may not necessarily be worth that. Okay. So let me actually talk about something called a residual. Here, I'll put it up top. Okay, a residual is equal to the actual. I know residual is one of those words that show up in random places in life, and here we're talking about the actual minus the predicted values, okay? Actual value minus predicted value. Okay? So let's say you buy a car that's 8 years old and it didn't cost you $11,655. The actual cost, okay? So actual cost it's like Price is Right. Actual cost of 8-year-old car that you buy maybe was only $10,500. Okay? What is the residual? The residual would be the actual value, 10,500, minus the predicted value, 11,655. So we get a residual of negative 1155. Is that good with everyone? Okay. And so in this case, we have a negative residual, which means the actual was lower than predicted. It's a good thing if you're the buyer, bad thing if you're the seller. Okay? So depending on whether you want the actual to be higher or lower than what we predict, that's whether you get a negative or positive residual. So in this case, we have a negative residual, which means the actual cost was lower than what we predicted. Okay? Let's say actual cost of a 2-year-old car was $19,500. Okay, what is the residual here? Residual would be $19,500 minus $18,945, and you get, you know what, $555, something like that. Okay, and here we have a positive residual. The actual is higher than the predicted. How's that? Yay?
Yes.
Great. And copy all of this again. Actually, we're going to cut out the residual stuff. Someone's going to ask me to go back a slide, I know it. That's okay, I'm prepared. Or maybe we're good. All right, what is... Go back a slide, please. All right, what is the slope in this, in our equation? The slope is negative 1215, okay? Negative 1215. Okay, because we have to remember we're at y hat is equal to a plus bx. So we're expecting a positive. If we get a negative, then our slope is negative. Okay? What is the interpretation of our slope?
Like a negative positive value?
Yeah, so the interpretation of the slope is how much we predict y to change if x changes by 1. So what does that mean in the context of our problem? Okay, so the generic definition, which would be how much we predict y to change. So this is the definition when x changes by 1. So in this problem, what does it mean? It's how much we predict what to change. Yeah, we predict the value of the car to what? Go up or down or what? To go down, how much? Go down by $1,215 if the age goes up by 1. Goes up by 1 year. Okay. So, in other words, it's how much the value of the car drops for every year. How much value of car drops for each year. That's the interpretation of this slope. Is that good with everyone? Okay. So on next week's quiz, I'll probably present you with some kind of regression equation, and I'll ask, what is the interpretation of the slope? And you'll have different multiple choice answers, and you want to make sure you pick the correct one. Just like every other multiple choice question. To win the game, you must score more points than the other. Generally. Unless you're playing darts or something or whatever. Okay. So that is the slope. What is the intercept? Intercept is 21375. And what is the interpretation?
That's 0 years old.
Yeah, so if a brand new car or a car that's 0 years old, we predict to have this much value, okay? We predict a car that is 0 years old to have a value of 21375, okay? And in this context, or in this problem, it makes sense, okay? Because we can imagine a car that is 0 years old, okay? If we were trying to predict the value of a car based on, I don't know, the weight of a car, which is probably a terrible way to make predictions for the value of a car, it would not make sense to have a weight of 0. Yes, question?
What does that say at the very bottom before 21375?
Value of, or intercept?
Oh,
Intercept.
And the first one is interpretation of the slope.
Interpretation of the slope, question mark. How much we predict y to change when x changes by 1. How we feeling? Good? I got a thumbs up. 1. Better than none. All right.
Can you go back for 1 second?
Yes. Absolutely. See, I used to use the chalkboard. If I erased it, no going back.
You gotta get some.
I'm starting to like it more and more. In the beginning, it was a little awkward, but
Did you film yourself on the actual film?
I did film myself with the chalkboard also. It was very exciting. You could see me age through the years if you go back on my YouTube channel. Nah, yeah, whatever. Okay. Somewhere along the way, I decided to wear only red shirts to class, and I don't know when that happened. That was, I call this the red years of my life, and okay. All right, let's keep going on here. Okay, so we've talked about the interpretation of the slope. Okay, so maybe just one important thing. Let's talk about the independent and dependent variables. So sometimes in the description of a problem, it's not clear what the independent and dependent variables are, okay? The independent variable is the variable that we are using to make a prediction, okay? So we use this variable to make a prediction. It's also called the predictor. The dependent variable is the variable we are trying to predict. And it is known as, also called, the response. Okay? So is the independent variable the x or the y? Yeah, independent variable is the x, and the dependent variable is the y. Okay? So as you read a problem, you have to ask, which variable are we trying to predict? That you will assign as your y variable or your dependent variable, okay? So always ask which variable are we making predictions for? Okay, that variable will be y. Okay, so if I write a problem here, and I write okay, we recorded the math SAT scores of many students. We also recorded their GPA in their first year of college. Okay, we want to create a regression line based on this data. Okay, we hope to predict the performance of students in college based on their SAT scores. So I'll let you guys write that down, and don't shout it out, but choose which one should be the x variable and which one should be the y variable. What is x? What is y? Okay, keep in mind the data that you have recorded, because basically you can only make use x and y based on the data you've recorded as well. So. Okay, so what is our x variable and what is y?
X variable is the GPA for the first year.
Okay, so all right, we're trying to predict the performance of students in college. How do we measure the performance of students in college? GPA in their first year of college, okay, based on their SAT scores, okay? So we are using what to make the prediction? Yeah, so SAT, math SAT is the x, and the y is first year GPA. Okay, because we're trying to predict performance of students in college, which will be their GPA, based on their SAT score, okay? So that will be the math SAT. Yes, question.
Yeah, can you think of y as the quantity of interest?
Yes, y could be the quantity of interest, the response, I don't know.
But would it ever not be the quantity of interest?
Well, generally you're interested in both variables, both x and y, because you're looking for a relationship between x and y. So you're generally interested in both and how they relate to one another, but usually you're going to use one to make predictions for the other. Okay, you want to see how one depends on the other. Okay. Let me just check your homework assignments and make sure I've covered everything for your homework. Okay, so I think, okay, so just one more thing, okay? Or do I need to go back? Are we okay? Okay. One last thing. All right, so just some warnings. Okay. So linear regression is a very useful tool. Okay. But like every other useful tool in life, if not used properly, it can cause harm. Okay, so most useful thing in your kitchen is probably it's the knife, right? You chop up your vegetables and meat and whatever. It's hard to cook without a knife. It could also be used for harm if not used properly. So linear regression is a very useful tool, but don't mess up, or don't mess it up. Okay, don't use it for wrong things. Okay, so a few things. Do not use it. We've already covered this one. Do not use it for nonlinear relationships. Okay, we've already covered this. Okay. Do not use it to make predictions outside of the range where you've collected data. So what I mean by that is, let's say you have data right here, okay? And so you fit a regression line like this, okay? But lo and behold, you've only collected data basically up to here, okay? So you've collected data from here to here. Okay? So don't try to predict out here. Does that make sense? So a silly example. Let's say you've been tracking the height. You have a child and you've been tracking his height over the course of time. Okay? And it seems every year he gets older, he grows an inch. Okay? And this has been true since he was age, as a child, he's grown up. He's now 11 years old. And every single year that's gone by, he's grown at least an inch, okay? And so you can be like, oh man, at this rate, by the time he's 70 years old, he's going to be, 15 feet tall. That would be very silly, because even though the data shows in the range that you've collected a certain trend, that trend may not hold where you haven't collected data. And we know that as adults, after you reach age 20 or so, you're not going to really grow anymore, and so that's not gonna work. Okay, so silly example: child growth data cannot be used to predict his height at age 70. All right, other warnings. Watch out for outliers. Okay, so linear regression tries to fit data points. So let's say you've got points that look like this. So here, what would you say R is equal to? Yeah, it looks like R is equal to 0. So maybe this is the shoe size versus IQ, right? Big feet, high intelligence, big feet, low intelligence, small feet, high intelligence, small feet, low intelligence. You got all sorts, there's no correlation, okay? I'm going to add a data point, okay? There is, you get Bozo the clown has huge feet, abnormally large feet, okay? And he is actually very smart, okay? So he is something like here, okay? When you have this data point, suddenly it tries to fit this outlying point, okay? So this outlier influences the regression. Okay, so this is Bozo the clown, big feet, high intelligence. Bet you didn't know he was really, really smart. Okay, with a name like Bozo, you wouldn't expect that. All right, so so now you have the regression would suddenly think, oh, larger shoes mean higher intelligence. Okay, so regression would lead to the wrong conclusion that larger shoes are associated with high IQ scores. Okay. You know what they say about big feet? Big shoes. Okay. So there we go. That's all I've got. So good luck with your homework. We'll see you guys.